Part 1. A general overview. Think of your computer's hardware, like the screen, keyboard, processor, and memory, as powerful instruments. The operating system, OS, acts as the skilled conductor, orchestrating these components to work in harmony. It transforms raw power into a seamless experience, enabling your favorite applications, like web browsers and video games, to run smoothly and efficiently. The OS has two main jobs. First, it's a resource allocator. Think of it like a manager, deciding which program gets to use the computer's brain, called the CPU, how much memory each program gets, and when they can access your files. Its second job is to be a control program. This means it acts like a referee, making sure that all the different programs play nicely together and don't cause errors or crash the whole system. To do its job, the OS relies on something called interrupts. An interrupt is simply a signal sent to the processor that says, "Hey, I need your attention." This could be you typing on the keyboard, a program finishing a task, or an error occurring. It's the mechanism that lets the OS stop what it's doing and handle what's important right now. The core of the operating system is called the kernel. Think of the kernel as the OS's inner circle, the part that handles the most critical tasks. There are two main design philosophies for kernels. A monolithic kernel is like having all your experts in one big room. It's very efficient because they can talk to each other quickly, but if one part has a problem, it can affect everyone. On the other hand, a microkernel is like having a small manager who delegates tasks to different experts in separate rooms. This is more modular and secure, but communication between them is a bit slower. Most modern operating systems, like Windows and macOS, use a hybrid of both approaches. Finally, programs need a way to ask the OS for help, for instance, to read a file or display something on the screen. They do this using system calls. You can think of a system call as ringing a bell for service. The list of all available services is called the Application Programming Interface, or API. It's like a menu that tells programmers what services they can request from the OS. So, the key takeaway here is the operating system is the essential software that makes computers work, managing all the hardware and providing services to applications in a structured and efficient way. Part 2. Managing processes. When you run a program, like opening a web browser, the OS creates what's called a process. A process isn't just the program's code, it's the active instance of that program, with its own memory and resources. It's the difference between a recipe on a card and actually cooking the dish in the kitchen. To keep track of everything, the OS uses a process control block, or PCB. This is like a digital ID card for each process, holding all its vital information: what state it's in, is it running, is it waiting for something, how much CPU time it's used, where its memory is, and so on. Since you likely have many processes running at once, but only a few CPU cores, the OS has to be smart about sharing. It constantly performs a context switch. This is where the OS quickly saves the progress of one process, loads the progress of another, and lets it run for a brief moment. It does this so fast that it creates the illusion that all your programs are running at the same time. Sometimes a single process needs to do multiple things at once. This is where threads come in. A thread is a lightweight unit of execution within a process. For example, in a word processor, one thread could be checking your spelling while another is saving your document in the background. Because they are part of the same process, they can share data easily, making them very efficient for parallel tasks. And to decide which process or thread gets to run next, the OS uses scheduling algorithms. These are different strategies, like first come, first served, or a round-robin approach, to ensure the system runs smoothly and feels responsive to you, the user. The main idea here is the process is the fundamental unit of work, and the OS's job is to create, schedule, and manage these processes and their threads to allow for multitasking and efficient use of the computer. Part 3. Keeping processes in sync. When you have multiple threads or processes working together and sharing data, things can get messy. Imagine two threads trying to update your bank account balance at the exact same time. This can lead to what's called a race condition, where the final result depends on who gets there first, often leading to a wrong answer. To prevent this, we need synchronization. The part of a program that accesses shared data is called a critical section. The challenge is to ensure that only one thread can be in its critical section at any given time. This principle is called mutual exclusion. Programmers use tools to enforce this. The simplest is a mutex lock. Think of it as a key to a room. A thread must acquire the lock, take the key, before entering its critical section, the room. Once inside, no other thread can get the key until the first one is done and releases the lock. A more advanced tool is a semaphore, which is like having a set number of permits. If you have a resource that can be used by, say, 5 threads at once, you can use a semaphore with 5 permits. A thread takes a permit to use the resource and returns it when it's done. But synchronization can lead to its own problems. The most famous is deadlock. This is a situation where 2 or more processes are stuck in a standoff, each waiting for a resource that the other one holds. It's like 2 people who won't hang up the phone until the other person hangs up first. They'll be waiting forever. The key lesson is, synchronization is absolutely essential for writing correct programs that do multiple things at once, but it must be handled carefully to avoid creating new and complex problems like deadlock. Part 4. Managing memory. A computer's main memory, or RAM, is where programs must be to run. Managing this memory is one of the OS's most complex jobs. The CPU generates what are called logical addresses, a sort of idealized view of memory from the program's perspective. The OS, with help from a piece of hardware called the Memory Management Unit, or MMU, translates these into physical addresses, which are the actual locations in the RAM chips. A major challenge is fragmentation. This is when memory gets broken up into small, unusable chunks. Think of it like trying to fit a large suitcase into a car's trunk that's already filled with lots of small shopping bags. Even if there's enough total empty space, there's no single spot that's big enough. To solve this, modern operating systems use a technique called paging. The idea is to break both logical memory, the program's view, and physical memory, the actual RAM, into small, fixed-sized blocks. Logical blocks are called pages, and physical blocks are called frames. This way, a program's pages can be stored in any available frames in RAM, even if they aren't next to each other. It's like breaking a large book into individual pages and storing them in any empty folder in a filing cabinet. But the real magic is virtual memory. This is a brilliant trick that allows the OS to make a program think it has a huge amount of memory all to itself, even more than the physical RAM available. It works by keeping only the necessary parts of the program in RAM and storing the rest on the hard drive. When the program needs a part that's on the drive, the OS quickly brings it into RAM, a process called demand paging. If there's no room, the OS uses a page replacement algorithm to decide which page in RAM to kick out to make space. The takeaway is, modern memory management, through paging and virtual memory, allows for efficient, flexible, and secure use of memory, enabling us to run large, complex applications that would otherwise not fit in physical RAM. Part 5. Managing storage. Everything that needs to be kept long-term, your documents, photos, and the OS itself, is stored on secondary storage devices, like a traditional spinning hard disk drive, HDD, or a faster, more modern solid-state drive, SSD. For HDDs, which have a physical read-write head that moves across spinning platters, the OS uses disk scheduling algorithms. The goal is to optimize the order in which file requests are handled to minimize the physical movement of the head, which is the slowest part of the operation. This is like a smart elevator that plans its stops to pick up the most people in the most efficient path, rather than just going up and down for every single request. For reliability and performance, many systems use RAID, which stands for Redundant Array of Independent Disks. RAID combines multiple physical drives into one logical unit. Different RAID levels offer different trade-offs. For instance, one level might mirror all your data onto two separate drives, so if one fails, your data is still safe. Another level might spread your data across multiple drives to speed up reading and writing. Finally, the storage drive is also used for swap space. This is the area on the disk where the OS temporarily places memory pages that have been kicked out of RAM by the virtual memory system. In short, the OS manages long-term storage by using clever scheduling to optimize performance and technologies like RAID to improve reliability, all while supporting the virtual memory system. Part 6. The file system. To you, the user, the most visible part of the OS is the file system. It's what organizes all the data on your storage drives into a familiar structure of files and folders, which are technically called directories. The file system hides all the complexity of where the bits and bytes are physically located on the disk and gives you a simple, logical way to interact with your data. Behind the scenes, the file system has to keep track of a lot of information for each file, known as metadata. This includes things like the file's name, its size, who owns it, and who has permission to access it. There are different strategies for allocating space to files on a disk. One is contiguous allocation, where the entire file is stored in one continuous block. This is fast to read, but it can suffer from the fragmentation problem we discussed earlier. Another is linked allocation, which stores a file as a chain of blocks scattered across the disk. This is flexible, but can be slow if you need to jump to the middle of the file. A common modern approach is indexed allocation, which uses a special block called an index block that contains pointers to all the other blocks a file uses. This gives you fast, direct access without the fragmentation issues. To make the system more robust against crashes, many modern file systems use a technique called journaling. Before making any changes to the file structure, the OS first writes a log of what it's about to do in a special area called a journal. If the computer crashes mid-operation, the OS can read the journal upon rebooting and either complete the operation or undo it, ensuring the file system remains in a consistent, uncorrupted state. The main point is, the file system creates the organized, reliable, and user-friendly structure of files and folders we all rely on, managing the complex details of data storage for us. Part 7. Security and Protection. Now let's talk about keeping your computer safe. In operating systems, we often distinguish between protection and security. Protection refers to the internal mechanisms that control access to resources. For example, a protection mechanism ensures that one user's process cannot interfere with another user's process. Security, on the other hand, is the external problem of defending the system against unauthorized access and malicious attacks, like viruses or hackers. A good protection system is the foundation for good security. A core concept here is the principle of least privilege. This states that any program or user should only be given the bare minimum permissions needed to do their job. This way, if a program is compromised, the potential damage is limited. To enforce this, operating systems can use a concept called an access matrix. You can picture a big grid where the rows represent users or processes and the columns represent resources like files or devices. Each cell in the grid specifies what that user is allowed to do with that resource, for instance, read, write, or execute. There are two major models for access control. Discretionary access control, or DAC, is the one most of us are familiar with. It means the owner of a file can decide who gets to access it. A more rigid model used in high-security environments is Mandatory Access Control, or MAC. Here, the operating system itself enforces a system-wide policy, and not even the file's owner can change it. Of course, a huge part of modern security is cryptography, which is the art of using mathematical codes to protect information. It's used for confidentiality, to keep your data secret, for authentication, to prove you are who you say you are, and for integrity, to ensure data hasn't been tampered with. The key takeaway: protection mechanisms are the tools the OS uses to control access, while security is the broader policy of defending against threats. The principle of least privilege is a fundamental strategy in building a secure system. Part 8. Advanced and Modern Topics. The world of operating systems is always evolving. Two huge modern developments are virtualization and distributed systems. Virtualization is the technology that allows you to run multiple, separate operating systems on a single physical computer at the same time. Each of these is called a virtual machine, or VM. A special piece of software called a hypervisor, or a virtual machine manager, VMM, sits between the hardware and the VMs, managing resources and keeping each VM isolated from the others. This is the technology that powers cloud computing, allowing companies like Google and Amazon to run thousands of customer servers on their massive hardware infrastructure. The other major topic is distributed systems. A distributed system is a collection of computers that are networked together to work on a common task, but they don't share memory or a clock. The entire internet is a giant distributed system. A key challenge here is communication and coordination. A common example is a distributed file system, or DFS, which allows you to access files stored on remote computers as if they were on your own local machine, creating a seamless experience across a network. The lesson here is, technologies like virtualization and distributed systems have fundamentally changed computing, allowing for massive scalability and resource sharing, but they also introduce new and complex challenges in management and coordination. Part 9. Real-world case studies. Finally, the book looks at how these concepts are applied in the real world by examining two major operating systems, Linux and Windows. Linux is a famous open-source operating system. It is highly modular, meaning it's easy to add or remove features through what are called loadable kernel modules. For scheduling processes, it uses a sophisticated algorithm called the Completely Fair Scheduler, or CFS, which aims to give every process a fair slice of CPU time. Windows is the dominant commercial operating system from Microsoft. It has a complex, layered architecture and uses a scheduling algorithm based on priority levels, ensuring that important system tasks are always taken care of promptly. Its primary file system, NTFS, is very advanced and includes features for compression, encryption, and journaling right out of the box. The takeaway from these case studies is, real-world operating systems are incredibly complex. They often use hybrid designs, borrowing the best ideas from different theories to create a practical, high-performance system that meets the needs of millions of users. That's all for this episode of Geek Capsule. We hope it gave you a fresh perspective on the world of technology. We'd love to hear your thoughts, so feel free to leave a comment or share your feedback. If you enjoyed the show, don't forget to subscribe and join us next time for another essential read. Until then, keep your curiosity sparked and your mind open.